Hello again, this is Greg Stitt from the University of Florida. In this video, I'm going to follow up on the previous video where I showed how to create RTL code to implement a simple memory mapped register over the Core Cache Interface protocol. Basically, I explained the code that's used in the GitHub repository here for the CCIP MMIO example for the Intel Platform Acceleration Card. Now in this video, I'm going to follow up on that by explaining how to create the C++ code that would interface with that AFU that we created in the last video. So there's a lot of ways we could potentially do this. So Intel gives you the capability of communicating with an AFU with their OPE API, which has both a C and a C++ API. Now that API is very flexible. It gives you every mechanism you would need to implement pretty much whatever form of communication you would want. But because of that flexibility, it's also a little complex, so it can be overwhelming to learn at first. So what I have done for these training modules is created a C++ wrapper class that I just call AFU that hides most of the complexity of that API and provides you with the functionality that you will probably need 99% of the time. And then if you need something more complex, you can go and look at the details of the OPE API and modify the wrapper class to do something specific for your application. All right, so let's take a look at how this is going to work. I have just kind of skeleton code here. I'm going to fill in basically the code that you would find in the actual tutorial on the repository. My code today might be slightly different, but it's the same basic idea. So even if you understand what I'm doing, I'd still recommend referring to the repository code because it is well documented. Okay, so just stepping through this, I have kind of an empty main file here, and I have a header file here that includes this AFU JSON info.h. So if you remember from the presentation where I explain how AFUs work, there is some shared information in the C++ code and the RTL code that you specify in a JSON file where the Intel's simulation and synthesis scripts will automatically generate the corresponding headers from that JSON file. So this is the header that is automatically generated. So in fact, if you pull up a console, you will notice that it does not actually, let's do this. You'll notice that it does not actually exist in this directory. So let me do a make clean. Let me make it. But yet it still makes, despite the fact that this header file is obviously needed for the make and it isn't in our directory. Well, if you were to read through this make file, I'm not going to spend time doing that because it's kind of outside the scope of this lecture. But if you were to go into this obj directory, you will see that there is in fact a header file in there. And I will open that up here. And you'll see that there's a bunch of constants here that get automatically generated. This is all based off of information that was provided in the AFU JSON file. So nothing special you have to do there. All right, so now in main, we're going to basically interface with the FPGA now, or the AFU inside the FPGA. And the way we do that with the wrapper class that I created is that wrapper class is called AFU. So we're just going to create an instance of that wrapper class. We'll just call the instance AFU. And then we have to specify what AFU we want to use in the FPGA because there could potentially be many different AFUs in existence. We don't know which one's loaded in the FPGA at a given point in time. So we want to request the one that is specific to our application. And we do that through that universally unique identifier. And that is what is one of the pieces of information that is specified in this header file here. And so really this sharp define here is what we want to use. So right here, I'm just going to say AFU excel UUID. And now what this does, if you were to open up the code for this class, it basically uses the OPE API to find an AFU with this accelerator, get access to that accelerator, get a handle to that accelerator. All of that is hidden from you now. And basically, you just create an instance of this AFU object. Now, there are a bunch of issues exceptions and problems that can arise while doing this. For example, if you're requesting this AFU and it doesn't exist, or it's not loaded into the FPGA, or if the FPGAs in your system are busy, there's exceptions that can occur that can cause the construction of this AFU instance to fail. And so I've implemented a bunch of exception handling inside the wrapper class to make this a little bit more transparent. So basically, there's various things we have to catch. So I won't explain these in a bunch of detail, but you can read through the code for the AFU wrapper class if you want to see exactly how that works. But one of the types that is thrown as an exception is this FPGA result type. And Intel essentially gives you a way of printing out a somewhat meaningful error message based off of whatever this value E happens to be. So there's this FPGA error string. Well, that code provided by Intel will essentially convert whatever this E object is into an error string, and so you can print it out. So we could do something like that. Now, if you look through the code I posted to the actual repository, it does a lot more with this because, well, I said somewhat meaningful error message here. They're not that meaningful. It basically tells you what the error was, but if you want to provide a more meaningful error message, you can basically do things like if E is equal to FPGA busy, then you can print out a message saying, you know, all the FPGAs are busy or something like that. So it's a little bit more human readable if you do it that way. But I want to keep this video as short as possible to get across the main point, and so I'm going to skip that for now. So what are the other types we have to catch? Let's see, there are some just kind of general runtime errors that can be thrown in various situations. And those actually have a string associated with them. So in that case, you can basically do e.what, and that will essentially return a string that is defined when the error is thrown. So let me pull up an example of that just so you see what I'm talking about. So right here, for example, so if you try to create an instance of the AFU object using an FPGA handle that is null, then it'll basically say, you know, it'll throw an error saying you can't construct it with, it's a generic runtime error. Here's another one down here. If you try to read or write from the FPGA, read or write a 64-bit value and you provide it with an odd address, that will cause problems, so it throws a runtime error, things like that. And then finally, there is also a specific type that is thrown, that is part of the OPE object hierarchy. So there is this NoDriver error type, and essentially if you try to run this code on a system that doesn't have a driver installed for the FPGA, it's going to throw this error. And so you could print a message saying something along the lines of, you know, no FPGA driver found. Something like that. All right, so that essentially catches all the possible errors that can occur when we instantiate this AFU. The really nice thing about this wrapper class is after you've instantiated the AFU, communicating with the FPGA is really simple. There is basically a read and a write function. So I can basically say AFU.write and write to the FPGA, and likewise I can do AFU.read and read from the FPGA. So they're a little bit more complex than that, so let's take a look at the parameters that we need to specify. So when we do a write, the first parameter is the address, the memory mapped address that we want to write to. So what I can do is define some kind of constant. So up here, I'll basically say and if you remember from the previous video, the memory map register we implemented in the AFU had an address of 0020. So we want to make sure we use that same address in software, otherwise it will not work. And ideally what you would do is, since this information is technically now shared between software and the AFU, ideally you would put all of this shared information in another JSON file and have it auto-generated when you compile. If you want to do that, that's great. I'm not going to do it for the simple example, but if you're starting to get up to something where you have 1,000 registers, it can be really easy to mess up the address in one file and not the other. So if you have it in a JSON format and auto-generate all of this kind of constant code right here, then you avoid those coherency issues. All right, so now we're going to write to this user register, or the address of that user register. And let's just say for now, we're going to write the value 5. Now, we want to read back from that same register to see if it worked. So we could essentially do something like this. We read from that address again, and we store it into this value here. And we could basically check to see, if I is not equal to 5, then there was some kind of error. Okay, so this is not the greatest test. If you look at the example I have posted on the repository, I basically put this all into a loop. In fact, I can do that really quick. So technically we're reading and writing 64-bit data. So I'll use a 64-bit unsigned type here. And I think what I do on the tutorial is I just test the writing and reading of 100 different numbers to our register. And then I would do AFU write. Every single time we're going to write to the same user register. And I'm going to write the value of I. So I'm basically going to write 0 through 99 to this register. I am going to read a 64-bit result. And then I think I'll do something along the lines of if the result that I read is not equal to I, which was the value that we wrote into the register, that means the communication is not working correctly. Then I basically increment some error count. So up here, I could do something like this. And then down here, I could essentially check to see if errors is greater than 0. If it is, I could basically print something along the lines of memory mapped IO tests failed. And then just follow normal practices and return a failure code. Otherwise, I can basically say that all the tests succeeded. I don't know why I'm having a hard time typing here. And do something like that, where if I don't have any errors, then it obviously worked. All right, so let's compile this first to make sure I don't have any mistakes, because I probably do. Oops, wrong directory. All right, so actually I don't have any syntax errors. Now, what I'm going to do is simulate this, and I'm not going to explain the simulation in this video. So for now, just bear with me, and in a separate video, I will explain exactly how the simulation is working. So just know that what I'm doing right now is basically running the executable that was just compiled. And I should point out there are two different executables, at least with this makefile. There's different ways of doing this, but the way I've configured this makefile is to output two executables. So one is AFU. That's the one we would run if we were actually running this on the FPGA. Now, if we want to simulate it, there's a separate executable called AFU_ASE. So ASE is Intel's simulation environment. It just stands for AFU simulation environment. And that does hardware-software co-simulation, which is very useful. So that is what I'm going to do right now, because I'm not currently logged onto a system that has this FPGA installed. So I'm going to run the simulation version of this. And in the background, I have the simulation already set up with all the RTL code. And when I run this, you see it prints out that all the tests succeeded. So this did in fact work. Let's see. One thing I guess I can show you real quick. That has to finish reinitializing the simulation. I'll just point this out now because it's super useful. So you'll notice I have this ASC log equal to 0 before I ran the executable. So that sets an environment variable that tells the simulation within ASC to not output a ton of logging information. So you'll notice there's a little bit where basically it says it's initializing the simulation and then doing some cleanup afterwards. If I run it without that log information, you'll see basically everything that's communicated across CCIP, you see logged during the simulation. Now that can be really useful if you're trying to debug, but at the same time, if you're running something that takes a very long time to run, it can be kind of overwhelming to deal with all of that logged information when you're looking for messages like this. So that's about it for the AFU wrapper class. I will be adding functionality to this in subsequent videos. And I encourage you, if you want to learn about the OPE API itself, to read through this afu.cpp file. It's commented reasonably well, and I explain what's going on throughout all of here. And Intel has a bunch of examples that use the OPE API itself. But for now, I would encourage you to just use this AFU wrapper class, since all you really have to do is instantiate or create an instance of the AFU class, specify the ID of the AFU you want to use, and then call these read and write functions to communicate over CCIP. And that's about as simple as you can get. All right, so that's it for this video. And I will have follow-up videos on how to do the simulation, which I did in this video, I just didn't explain it. There's a lot to it, so I need an entire video for that. I will then show you how to synthesize the RTL code that we created in the earlier video, and then I'll finally show you how to actually run this on a system with an Intel pack installed so you can actually see it working on the FPGA.